ಎಲ್ಲರಿಗೂ ಸ್ವಾಗತ. ಈ ವಿಡಿಯೋದಲ್ಲಿ ಕ್ರೋಮ್ಯಾಟಿಕ್ ಪಾಲಿನಾಮಿಯಲ್ ಬಗ್ಗೆ ಡಿಸ್ಕಸ್ ಮಾಡೋಕೆ ಹೋಗ್ತಾ ಇದ್ದೀವಿ. ಸೊ ನಮ್ಮ ಪ್ರೀವಿಯಸ್ ವಿಡಿಯೋಗಳಲ್ಲಿ ಕ್ರೋಮ್ಯಾಟಿಕ್ ನಂಬರ್ ಅಂದರೆ ಏನು, ಅದರಲ್ಲಿ ಎರಡು ಥರ ಬರುತ್ತೆ. ವರ್ಟೆಕ್ಸ್ ಕ್ರೋಮ್ಯಾಟಿಕ್ ನಂಬರ್ ಮತ್ತು ಎಡ್ಜ್ ಕ್ರೋಮ್ಯಾಟಿಕ್ ನಂಬರ್. ವರ್ಟೆಕ್ಸ್ ಕ್ರೋಮ್ಯಾಟಿಕ್ ನಂಬರಲ್ಲಿ ನಾವು ಯೂಶ್ವಲಿ ವರ್ಟೆಕ್ಸ್ ಅನ್ನೋ ವರ್ಡನ್ನು ಯೂಸ್ ಮಾಡೋಕ್ಕೆ ಹೋಗಲ್ಲ. ಜಸ್ಟ್ ಕ್ರೋಮ್ಯಾಟಿಕ್ ನಂಬರ್ ಆ್ಯಂಡ್ ಎಡ್ಜ್ ಕ್ರೋಮ್ಯಾಟಿಕ್ ನಂಬರ್. ಸೊ ಬರೀ ಕ್ರೋಮ್ಯಾಟಿಕ್ ನಂಬರ್ ಅಂತ ಹೇಳಿದ್ರೆ ದಟ್ ಈಸ್ ಅಂಡರ್ಸ್ಟುಡ್ ದಟ್ ವಿ ಆರ್ saying about vortex chromatic number. So two types of chromatic numbers we have studied in our previous videos: chromatic number or vortex chromatic number. Another one is edge chromatic number. So chromatic number andre no, suppose you have a graph, let G be any graph. Now assigning colors to vertices of this graph is called coloring of G. Assigning colors to the vertices of G is called coloring of G, and that coloring is said to be proper if two adjacent vertices receives different colors. So coloring ಅಂತಂದ್ರೆ ಅಲ್ಲಿರೋ ವರ್ಟೈಸಸ್ಗೆ ಬರೀ ಕಲರ್ ಅಸೈನ್ ಮಾಡೋದಷ್ಟೇ. ಸೊ ಪ್ರಾಪರ್ ಕಲರಿಂಗ್ ಅಂತಂದರೆ ಇಟ್ ಹ್ಯಾಸ್ ಟು ಸ್ಯಾಟಿಸ್ಫೈ ಅಡಿಷನಲಿ ಒನ್ ಕಂಡೀಷನ್. ವಾಟ್ ಇಸ್ ದಟ್ ಕಂಡೀಷನ್? adjacent vertices should receive different colors. No two adjacent vertices should have same color. So proper coloring ಅಂತ ಹೇಳ್ತೀವಿ ಅದನ್ನು. So the minimum number of colors that are required to properly color a graph is called chromatic number. The minimum number of colors that are required to properly color a graph is called its chromatic number. So chromatic number of a graph is denoted by chi of G. So the same concept will extend to edges of G. So ಒಂದು ಗ್ರಾಫ್ ಅಂತಂದರೆ ಎರಡು ಪ್ಯಾರಾಮೀಟರ್ ಇರುತ್ತೆ ಯೂಶ್ವಲಿ, ವರ್ಟೈಸಸ್ ಇನ್ನೊಂದು ಎಡ್ಜಸ್ ಅಂತ. ಸೊ ವರ್ಟೈಸಸ್ಗೆ ಏನು ನಾವು ಡೆಫಿನೇಷನ್ ಡಿಫೈನ್ ಮಾಡಿದ್ವಿ, ಸೇಮ್ ವಿ ಕ್ಯಾನ್ ಎಕ್ಸ್ಟೆಂಡ್ ಟು ಎಡ್ಜಸ್ ಆಲ್ಸೋ. ಸೊ ದ ಮಿನಿಮಮ್ ನಂಬರ್ ಆಫ್ ಎಡ್ಜಸ್, the minimum number of colors that are required to properly color edges of G is called edge chromatic number of G. This is chromatic number of G, chi of G notation. So edge chromatic number ke chi 1 of G. So this is edge chromatic number. Now we are okay with this properties, I mean definition and examples on that. Next we are going to discuss what is the chromatic polynomial of a graph. Now let us start with a graph again. Let G be any graph. G be any graph. ಒಂದು ಗ್ರಾಫ್ ಕೊಟ್ಟಿದ್ದಾರೆ ನಮಗೆ ಈಗ, ಆ್ಯಂಡ್ ಸಪೋಸ್ ದೇರ್ ಆರ್ ಎಕ್ಸ್ ಕಲರ್ಸ್. ಸಪೋಸ್ ದೇರ್ ಆರ್ ಎಕ್ಸ್ ಕಲರ್ಸ್. ಈಗ ಒಂದು ಗ್ರಾಫ್ ಇದೆ, ಒಂದು ಸೈಡಲ್ಲಿ ಒಂದು ಗ್ರಾಫ್ ಇದೆ, ಇನ್ನೊಂದು ಸೈಡಲ್ಲಿ ಎಕ್ಸ್ ನಂಬರ್ ಆಫ್ ಕಲರ್ಸ್ ಇದೆ. ಇಲ್ಲಿ ಎಕ್ಸ್ ಅನ್ನೋದು ಆ್ಯಕ್ಚುಲಿ ನಂಬರ್ ಡಿನೋಟ್ ಮಾಡ್ತೀವಿ. ದಿಸ್ ಆ್ಯಕ್ಚುಲಿ ರಿಪ್ರೆಸೆಂಟ್ಸ್ ನಂಬರ್. ಸೊ ದೆರ್ ಈಸ್ ಎ ಗ್ರಾಫ್ G on one side, and on the other side there are x number of colors. Now the chromatic polynomial, that is actually the polynomial denoted by p of G comma x. This is called chromatic polynomial of G. Chromatic polynomial of G. ಇಲ್ಲಿ chromatic polynomial ಅಂತಂದರೆ ಯೂಶ್ವಲಿ ವರ್ಟೆಕ್ಸ್ ಕ್ರೋಮ್ಯಾಟಿಕ್ ಮಾತ್ರ ಡಿಸ್ಕಸ್ ಮಾಡ್ತಾ ಹೋಗ್ತೀವಿ. ಎಡ್ಜ್ ಕ್ರೋಮ್ಯಾಟಿಕ್ ಪಾಲಿನಾಮಿಯಲ್ ಇಲ್ಲಿ ಡಿಸ್ಕಸ್ ಮಾಡ್ತಾ ಇಲ್ಲ. ವಿ ಜಸ್ಟ್ ಡಿಸ್ಕಸ್ ವರ್ಟೆಕ್ಸ್ ಕ್ರೋಮ್ಯಾಟಿಕ್ ಪಾಲಿನಾಮಿಯಲ್ ಆರ್ ಸಿಂಪ್ಲಿ ಕ್ರೋಮ್ಯಾಟಿಕ್ ಪಾಲಿನಾಮಿಯಲ್. So the chromatic polynomial p of G comma x is a chromatic polynomial that represents, how many ways, okay, 1 minute, that actually represents number of ways anta tagona, that represents number of ways that G can be colored with at most x colors. So that is the definition of the chromatic polynomial. The chromatic polynomial of a graph represents number of ways that the given graph G can be colored with at most x colors. ಇಲ್ಲಿ ಏನು ನಂಬರ್ ಬರುತ್ತೆ? So this I have to write here, at most x color. So see, if I write P of G comma 2, that means number of ways that a graph G can be colored with at most 2 colors. ಎಷ್ಟು ರೀತಿಯಲ್ಲಿ ಆ ಎರಡು ಕಲರ್ನ ಅಸೈನ್ ಮಾಡ್ಬೋದು. ಸೊ ಎರಡು ಕಲರ್ನ ಒಟ್ಟಿಗೆ ಅಸೈನ್ ಮಾಡ್ಬೋದು ಅಥವಾ ಒಂದೇ ಕಲರ್ ಅಸೈನ್ ಮಾಡ್ಬೋದು, ಆ ರೀತಿ. ಸೊ ದರ್ ಮೇ ಬಿ ಮೆನಿ ಪಾಸಿಬಿಲಿಟಿ. ಸೊ 2 ಕಲರ್ಸ್ ತೊಗೊಂಡ್ರೆ ಯೂಶ್ವಲಿ 3 ಪಾಸಿಬಿಲಿಟಿ ಬರುತ್ತೆ ನಿಮಗೆ. ಸಪೋಸ್ ಈಗ ರೆಡ್ ಮತ್ತು ಬ್ಲೂ ಅಂತ ತಗೋತೀನಿ. ಸೊ ಫಸ್ಟ್ ಪಾಸಿಬಿಲಿಟಿ ಐ ಕ್ಯಾನ್ ಅಸೈನ್ ಓನ್ಲಿ ರೆಡ್ ಕಲರ್, ಅಥವಾ ರೆಡ್ ಬ್ಲೂ ಕಾಂಬಿನೇಷನ್ ತಗೋಬೋದು, ಅಥವಾ ಓನ್ಲಿ ಬ್ಲೂ. ಆ್ಯಂಡ್ ಇಟ್ ಮೇ ಹ್ಯಾವ್ ಸೋ ಮೆನಿ ನಂಬರ್ ಆಫ್ ವರ್ಟೈಸಸ್. ಸೊ ಚೇಂಜಸ್ ಆಗ್ತಾ ಹೋಗುತ್ತೆ ನಿಮಗೆ, ನಂಬರ್ ಆಫ್ ಪಾಸಿಬಿಲಿಟೀಸ್ ಚೇಂಜಸ್ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. So P of G comma 2 represents number of ways that G can be colored with 2 colors. That is the chromatic polynomial with x equal to 2. So generally x anta tagondre we have to write this notation. P of G comma x, the chromatic polynomial of G represents the number of ways that a graph G can be colored with at most x colors. Let us see some examples. First example, let us take only one example. I will take time being P3. Let G isomorphic to P3, and I need to determine P of G comma x. I have graph P3. I need to determine its chromatic polynomial P of G comma x. Now let us take P3. So this is the vertex V1, V2, V3. Okay now so there are x number of colors. So colors set till on ಬರ್ಕೋಣ. So okay, here are x number of colors. This is set of colors. Totally this has x number of colors. Now start from this vertex. I want to assign a color to this vertex. ಎಷ್ಟು possibility ಇದೆ? I can assign any one of this color to this vertex. So ಇಲ್ಲಿರೋ ಯಾವ್ದಾದ್ರು ಕಲರ್ ತಗೋಬೋದು. So suppose you have 10 colors here, then it has 10 possibility. Suppose you have 100 colors, then it has 100 possibilities. ಸೊ ಇಲ್ಲಿ ಎಷ್ಟು ಕಲರ್ ಇದೆ ಅಷ್ಟು ಕಲರ್ನು ಈಗ ಅಸೈನ್ ಮಾಡ್ಬೋದು, ಯಾವುದೇ ಕಂಡೀಷನ್ ಇಲ್ಲ. ಸೊ ಐ ಕ್ಯಾನ್ ಅಸೈನ್ ಎಕ್ಸ್ ನಂಬರ್ ಆಫ್ ಕಲರ್ಸ್ ಟು ದಿಸ್. ಪ್ರಾಪರ್ಲಿ ಕಲರಿಂಗ್, ಕೀಪ್ ದ್ಯಾಟ್ ಇನ್ ಮೈಂಡ್. ಬರೀ ಕಲರ್ ಅಸೈನ್ ಮಾಡೋದಲ್ಲ, ಪ್ರಾಪರ್ಲಿ ಕಲರಿಂಗ್ ಅಸೈನ್ ಮಾಡೋದು ತುಂಬ ಇಂಪಾರ್ಟೆಂಟ್. ಸೊ ಓಕೆ, ದಿಸ್ ಹ್ಯಾಸ್ ಎಕ್ಸ್ ಪಾಸಿಬಿಲಿಟೀಸ್. ನೌ ಕಮ್ ಟು ದಿಸ್ ವರ್ಟೆಕ್ಸ್. ಹೌ ಮೆನಿ ಪಾಸಿಬಿಲಿಟೀಸ್ ಆರ್ ದೇರ್ ಟು ಅಸೈನ್ ಎ ಕಲರ್ ಟು ದಿಸ್ ವರ್ಟೆಕ್ಸ್? This has x number of colors. Supposing now time being x equal to 100 ಅಂತ ಇಟ್ಕೋತೀನಿ. So now there are 100 colors here in this set, and you cannot assign a particular color that is assigned to V1 to V2. ಸೊ ಇಲ್ಲಿ V1 ಯಾವುದೋ ಒಂದು ಕಲರ್ ಕೊಟ್ಬಿಟ್ಟಿದ್ದೀನಿ, ಒಂದು ಕಲರ್ ಮೈನಸ್ ಆಯ್ತು. ಈಗ ನನಗೆ ಉಳ್ಕೊಂಡಿದ್ದೀನೋ 99 ಕಲರ್ಸ್. ಸೊ ಯು ಕ್ಯಾನ್ ಅಸೈನ್ ಎನಿ ಒನ್ ಆಫ್ ದಿಸ್ 99 ಕಲರ್ ಟು ದಿಸ್ ವರ್ಟೆಕ್ಸ್. ಹೌದಾ? ಈ ಕಲರ್ ಕೊಡೋಕ್ಕಾಗಲ್ಲ, ಯಾಕಂದರೆ ಪ್ರಾಪರ್ಲಿ ಕಲರ್ ಪಾಸಿಬಿಲಿಟಿ ಕಂಡೀಷನ್ ಫೇಲ್ ಆಗುತ್ತೆ. ಸೊ ದಿಸ್ ಹ್ಯಾಸ್ x minus 1 ಪಾಸಿಬಿಲಿಟಿ. Now come to this vertex V3. Now for V3 you can consider this color. Why? Because these two are non-adjacent. So ಇಲ್ಲಿ ಏನು ಕಲರ್ ಕೊಟ್ಟಿದ್ದು, ಸಪೋಸ್ ಇಲ್ಲಿ ರೆಡ್ ಕೊಟ್ಟಿದ್ರೆ I can take a red again. So you can consider this color, but you cannot consider the color that is assigned to V2. So ಈ ಕಲರ್ ನಾನು ತಗೋಬೋದು ಇಲ್ಲಿಗೆ ಪಾಸಿಬಿಲಿಟಿಲಿ. ಯು ಕ್ಯಾನ್ ಕನ್ಸಿಡರ್ ದಿಸ್ ಫಾರ್ ದಿ ಪಾಸಿಬಿಲಿಟಿ, ಬಟ್ ದಿಸ್ ಕಲರ್ ಯು ಕ್ಯಾನಾಟ್ ಕನ್ಸಿಡರ್ ಫಾರ್ ದಿ ಪಾಸಿಬಿಲಿಟಿ ಆಫ್ ಅಸೈನಿಂಗ್ ಎ ಕಲರ್ ಟು V3. ಸೊ ಅಗೇನ್ ದಿಸ್ ಆಸ್ ಟೋಟಲ್ ನಂಬರ್ ಆಫ್ ಕಲರ್ಸ್ ಮೈನಸ್ ಪ್ರಾಬ್ಲಮ್ ಕೊಡ್ತಾರೆ ಇದೊಂದಲ್ವಾ, ಅಗೇನ್ ದಿಸ್ ಆಸ್ x minus 1 ಪಾಸಿಬಿಲಿಟೀಸ್. ಸೊ ದಿ chromatic polynomial of G ಅಂತಂದರೆ P3, P of G, X the chromatic polynomial of P3 is x. So first vertex can be colored with x colors into x minus 1 into x minus 1. So that is x into x minus 1 whole square, andre x square minus 2x plus 1, or p of p3 comma x. ಅಥವಾ ನಿಮ್ಗೆ ಕನ್ಫ್ಯೂಷನ್ ಆಗುತ್ತೆ ಅಂತಂದರೆ ಯು ಕ್ಯಾನ್ ಜಸ್ಟ್ ರೈಟ್ ಜಿ p3 ಬೇಡ ಜಿ ಅಂತಲೇ ಬರ್ಕೊಳ್ಳೋಣ. ಇಲ್ಲೂ ಪಿ ಇದೆ, ಪಿ ಕನ್ಫ್ಯೂಷನ್ ಆಗ್ಬೋದು. ಸೊ ಎಕ್ಸ್ ಕ್ಯೂಬ್ minus 2x square plus x. I have multiplied this x inside. So this is the chromatic polynomial of P3. This is the chromatic polynomial of P3. So similarly we can define the chromatic polynomial of disconnected graph, totally disconnected graph, complete graph, and etc. So let us try some examples on this. Problems ಅಂತಲೇ ತಗೊಂಡು ಹೋಗ್ತೀನಿ. ಪ್ರಾಬ್ಲಮ್ಸ್ ಯೂಶ್ವಲಿ ನಿಮಗೆ ಏನು ಪ್ರಾಬ್ಲಮ್ಸ್ ಕೇಳಲ್ಲ. ಸೊ ಯೂಶ್ವಲಿ ಯು ವಿಲ್ ಬಿ ಗಿವನ್ ವಿತ್ ಎ ಗ್ರಾಫ್ ಆ್ಯಂಡ್ ಯು ವಿಲ್ ಬಿ ಆಸ್ಕ್ ಟು ಫೈಂಡ್ ಇಟ್ಸ್ chromatic polynomial. So A, determine the chromatic polynomial of the following graphs. Determine the chromatic polynomial of the following graphs. So ಒಂದೊಂದಾಗಿ ನೋಡ್ತಾ ಹೋಗೋಣ ಈಗ. So first one, so I'll take the totally disconnected graph. G isomorphic to Kn bar. So if I write just Kn, it is complete graph on invertices. I have written Kn bar here. See, this graph will be like this. It has no edges, and as usual I have a set of x colors. If you want, you can take x equal to some number, or just to avoid confusion. X ಅಂತಂದ್ರೆ usually variable ಅಂತ ನಮ್ಮ ಮೈಂಡಲ್ಲಿ ಇರುತ್ತೆ. So usually we treat x as variable. So to understand well, fix some quantity to that. X equal to some 100 or 2000, fix ಮಾಡ್ಕೊಳ್ಳಿ. Now let us start from this vertex. So this vertex has x possibilities. ಹೌದಾ? Because we are starting from this, that is the reason. ಇದೇ ಫಸ್ಟ್ ವರ್ಟೆಕ್ಸ್ ನಾವು ತಗೋತಾ ಇರೋದ್ರಿಂದ ಫಸ್ಟ್ ವರ್ಟೆಕ್ಸ್ಗೆ ಯು ಕ್ಯಾನ್ ಅಸೈನ್ ಎನಿ ಕಲರ್. ಫಸ್ಟ್ ವರ್ಟೆಕ್ಸ್ ಕ್ಯಾನ್ ಬಿ ಅಸೈನ್ಡ್ ವಿತ್ ಎನಿ ಕಲರ್, ನೋ ಪ್ರಾಬ್ಲಮ್ ವಿತ್ ದಟ್. ಸೊ ದಿಸ್ ಆಸ್ ಎಕ್ಸ್ ಪಾಸಿಬಿಲಿಟಿ. ಸಿನ್ಸ್ let vertex set of K and B, V1, V2, Vn, the vertex V1 as x possibilities, because we are starting from that vertex only. First vertex usually x possibilities irutte, so this has x possibilities. The vertex Vi I greater than or equal to 2, obviously I will be less than or equal to n. Also has now let us before writing this sentence come to this vertex. ಯಾವುದೇ ಒಂದು ವರ್ಟೆಕ್ಸ್ ಬನ್ನಿ ಇವಾಗ, except this one. So let us take this vertex. How many possibilities are there to this vertex to color it? No vertex is adjacent to this. ಇಲ್ಲಿರೋ ಯಾವ ವರ್ಟೆಕ್ಸ್ ಇದಕ್ಕೆ ಅಡ್ಜಸೆಂಟ್ ಆಗಿಲ್ಲ. ಸೊ ದಿಸ್ ಕ್ಯಾನ್ ಬಿ ಕಲರ್ಡ್ ವಿತ್ ಎಕ್ಸ್ ಕಲರ್ಸ್ ಓನ್ಲಿ. Since no vertex in the graph is adjacent to this, there is no issue of removing any color from the list. Adjacency, suppose these two are adjacents, then we have to rule out this color. But no vertex is adjacent, so again this can be colored with x colors. This can also be colored with x colors. this can also be colored with X colors. So each vertex can be colored with X colors. Why? Because none of two vertices are adjacent in Kn bar. So the vertex Vi, I greater than or equal to 2, also has X possibilities. As Kn bar has no edges. Therefore the chromatic polynomial of Kn bar is equal to n barata chromatic polynomial x into x into x into x into x. You have to go up to n vertices. So the chromatic polynomial is x power n. Chromatic polynomial of Kn bar comma x is equal to x power n. Yes. Now second graph. G isomorphic to obvious algorithm Kn. When we discuss Kn, we also discuss Kn bar. When we discuss Kn bar, obviously we discuss Kn. Now let us see what will be the chromatic polynomial of this graph. For example, we will take K5 bar. So here in the complete graph, every pair of vertices are adjacent. Okay. Now 4, 4, 4, 4. Okay. Now again we have a set of X colors. Now suppose this vertex receives first color. Suppose this receives X color. Then come to this vertex. This cannot receive the color that is received by this vertex. So this has to receive X minus 1 color. Now come to this vertex. See, this vertex is adjacent to these two, so it cannot receive the colors received by these two vertices. So this can receive, two colors are ruled out, so remaining are X minus 2. Now for this vertex, all these three vertices are adjacent, so 3 colors I have to rule out. X minus 3. Again here X minus 4. This you can write as X minus 0. Now if you want proof, solution, let the vertex set of K and B, V1, V2 and so on Vn. Since every pair of vertices are adjacent, the color received by a vertex will be reduced by 1 at each step. I am just writing this for your understanding. You can write the proof if asked in any way. Only thing is, it has to convey why the polynomial of that graph is the obtained one. See, then x minus 0 ito. Next illu 1 reduce ito. Next step it becomes 2, x minus 2. Then it becomes x minus 3. It becomes x minus 4. So it goes up to, if the graph has n vertices, then see it goes up to x minus 1, x minus 2, it can go up to only x minus of n minus 1, because n times it has to reduce, but it starts from 0. So n times antandre it stops at n minus 1. So that is we have the chromatic polynomial p of kn comma x equal to, see, in the first step it will be x. Prati step allo it should be reduced by 1. Second step x minus 1. Third step third vertex x minus 2. Fourth vertex x minus 3, and it goes up to nth vertex. See, first vertex x minus 0, second vertex x minus 1, third vertex x minus 2. So nth vertex x minus of n minus 1. So you can write x into x minus 1 into x minus 2 and so on, x minus n plus 1. So this is the chromatic polynomial of complete graph. That is the chromatic polynomial of complete graph. Next, let us see path graph. Generally P3 nodadvalva. So path graph, path Pn. So let us take 1, 2, 3, 4, 5, 6, P6 tagotane, and suppose you have, as I said, x colors. Now this vertex has x possibilities, first vertex, so it has x possibilities. So first vertex of, as usual, vertex set barkobedi first. Write down the vertex set, then write this. First vertex of Pn receives x colors, where the next vertex can receive at most ಎಷ್ಟು color ಕೊಡಬಹುದು ಈಗ. Now maximum of, see, one possibility will be ruled out of x, so we will be having x minus 1. At most x minus 1 colors, and this continues for each vertex, each vertex in the sense, see, if I take, suppose this vertex, don't worry about these vertices. What are the vertices you have already considered, only think of that. ಇಲ್ಲಿ x minus 1 ಇದೆ, I mean there is one color assigned to this vertex, one color is assigned to this vertex, and that should be ruled out from the list. So it gets x minus 1 possibilities. Again this also gets x minus 1 possibilities, x minus 1 possibilities, x minus 1 possibilities. So totally this graph path Pn, therefore chromatic polynomial of Pn is x into x minus 1 whole power n. N, okay, it is n minus 1, yes, it is not n, it is n minus 1. Now let us see star graph. See, a cycle graph is not that much easy. I am not going to prove cycle graph. I will just state the chromatic polynomial of cycle graph and wheel graph. That two are a bit difficult. So star graph. Star graph. So the graph looks like this. K 1 comma n ಅಂತ ತಗೋಣ. So this is 1 2 3 4 5 6, K 1 comma 6. Okay, now suppose as usual there are x colors. Now suppose we assign a color to this. This has x possibilities. This has x possibilities. Now come to this. Since these two are adjacent, one possibility will be ruled out of x. So this can receive x minus 1 colors. This also receives x minus 1 colors. This also has x minus 1 colors. X minus 1 colors, x minus 1 colors, and this x minus 1 colors. So you don't confuse this. This is actually the possibility for the center vertex. So for star graph also, k1 comma n allo tagondirodu generally here k1 comma 6. For star graph, you will be having p of k1 comma n equal to x comma x equal to, see what we get here, x into 1 2 3 4 5 6, x minus 1 whole power 6. So x into x minus 1 whole power n. So in fact it is a general result that generally for any tree graph, tree graph G, the chromatic polynomial of tree graph is x into x minus 1 whole power n minus 1 if G, order of G equal to n. See, ಇಲ್ಲಿ ನೀವು ಏನು ನಂಬರ್ ಬರೀಬೇಕಂದ್ರೆ ಟೋಟಲ್ ನಂಬರ್ ಆಫ್ vertices minus 1. ಇಲ್ಲೂ ಅಷ್ಟೇ ಅಲ್ವಾ. ಸೊ here total number of vertices is 7. So I mean 7, here I have written 7 minus 1. So ಇಲ್ಲಿ k1 comma n ಅಂತಂದ್ರೆ it will be having total number of n plus 1 vertices. So ಇಲ್ಲಿ n ಬಂದಿದೆ. ಸೊ ಕನ್ಫ್ಯೂಸ್ ಮಾಡ್ಕೋಬೇಡಿ, ಇಲ್ಲಿ n ಬರ್ದಿದ್ದಾರೆ ಮತ್ತು ಇಲ್ಲಿ n minus 1 ಬರ್ದಿದ್ದಾರೆ ಅಂತ. So total number of vertices minus 1 you have to write actually. So this is about star graph, I mean star graph and tree graph. So tree graph I think we have already discussed. So let us recall its definition and some important points about tree graph. See, any graph containing a cycle, is called cyclic graph. ಸೊ ಸೈಕಲ್ ಗ್ರಾಫ್ ಬೇರೆ, ಸೈಕ್ಲಿಕ್ ಗ್ರಾಫ್ ಬೇರೆ. ಸೈಕ್ಲಿಕ್ ಗ್ರಾಫ್ ಅಂತಂದರೆ ಆ ಗ್ರಾಫ್ ಒಳಗಡೆ ಒಂದು ಸೈಕಲ್ ಥರ ಸ್ಟ್ರಕ್ಚರ್ ಇರಬೇಕು. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ಸಿ ವಿ ಹ್ಯಾವ್ ದಿಸ್. See this graph, this is not a cycle, but see if I take this subgraph ABD, this is a cycle C3. So if a graph G contains a subgraph that is a cycle, then it is called a cyclic graph. ಅಥವಾ ಗ್ರಾಫ್ ಒಳಗಡೆ ಸೈಕಲ್ ಸ್ಟ್ರಕ್ಚರ್ ಏನಾದರೂ ಇದ್ದರೆ ಇಟ್ ಇಸ್ ಕಾಲ್ಡ್ ಎ ಸೈಕ್ಲಿಕ್ ಗ್ರಾಫ್. ಎ ಗ್ರಾಫ್ ಕಂಟೈನಿಂಗ್ ನೋ ಸೈಕಲ್, is called acyclic graph. Now suppose I remove this vertex A, I remove D, then this graph looks like, so ಇಲ್ಲಿ ನಮಗೆ ಸೈಕಲ್ ಸ್ಟ್ರಕ್ಚರ್ ಇಲ್ಲ, ಸೈಕಲ್ ಸ್ಟ್ರಕ್ಚರ್ ಹೋಗ್ಬಿಡ್ತು. ಯು ಕ್ಯಾನ್ ರೈಟ್ ಲೈಕ್ ದಿಸ್, ಯು ಕ್ಯಾನ್ ರೈಟ್ ಇನ್ ಎನಿ ವೇ ಯು ವಾಂಟ್. ದೆರ್ ಇಸ್ ನೋ ಸೈಕಲ್ ಸ್ಟ್ರಕ್ಚರ್ ಹಿಯರ್. This has no cycle structure, this also has no cycle structure. Such graphs are called tree graphs. Tree. So usually ನಮ್ಮ ಮರ ಯಾವ್ದಾದ್ರು ಮರ ನೋಡಿದ್ರೆ ಯಾವ ರೀತಿ ಇರುತ್ತೆ, ಸೇಮ್ ಸ್ಟ್ರಕ್ಚರ್ ಇರುತ್ತೆ. A connected acyclic graph, this is the precise definition of tree graph. A connected acyclic graph is called tree. Connected acyclic graph is called tree. See, here if you consider only this, it is a tree because it is connected and contains no cycle. Connected and contains no cycle, so it is a tree. Such graphs are called tree graphs. Then, as I asked a quiz, a collection of trees is called forest. A collection of trees is called forest. Here we look into the degree of each vertex. See, look into this. This vertex has degree 3 and actually it has maximum distance from here. Or you can take this. This has degree 3 and this has degree 3. You have to consider vertices of maximum degree. So such vertices are called roots of tree. A vertex of maximum degree is called a root. ಬೇರು ಅಂತ ಏನು ಮರ ಕೇಳ್ತೀವಿ ನಾವು, ಸೇಮ್ ಕಾನ್ಸೆಪ್ಟ್ ಇರ್ಬೋದು. is called a root of a tree. ಆಮೇಲೆ ಈ ಸಿಂಗಲ್ ಡಿಗ್ರಿ ವರ್ಟೆಕ್ಸ್ ಇದೆ ನೋಡಿ, these single degree vertices. So these are called leaves of tree. A vertex of degree 1, a vertex of degree 1 is called leaf. That is called a leaf. This is about tree. So finally, I'll just state the chromatic polynomial of cycle graph and wheel graph. I'm not going to prove or take any example of that. That will be slightly difficult. Just look into the formula or the polynomial of that graph. So fourth, I think fifth. The chromatic polynomial of Cn, cycle on n vertices, is x minus 1 whole power n plus minus 1 power n into x minus 1. So this is the chromatic polynomial of cycle. The chromatic polynomial of wheel W1 comma n is x into x minus 2 whole power n minus 2 minus of minus 1 power n minus 1 into x minus 2. So don't worry about the chromatic polynomial of wheel, but chromatic polynomial of Cn you have to note down. So these are about some information on chromatic polynomial of a graph. So only the definition and examples we have discussed, that is enough for your understanding. So in the next video we will discuss a few points on line graph, then timetable scheduling problem we have to consider. Thank you.